In this video, I will introduce you to a rotating display. I'm an electronics hobbyist and I've developed the display over the last 2 years or so. The display has the form factor of a compact disc. The diameter of the discs is about 120 millimeters. The display consists of two main sub-assemblies. The one is the power supply, which is down here, and the other one is the display itself. The power supply transmits power wirelessly to the display disc. The display disc has 2 rows of LEDs with 20 LEDs each. So in total it's 40 LEDs. These LEDs are controlled by an Arduino microcontroller, which sits down here. Furthermore, there is an ESP01S microcontroller. This microcontroller generates the image information, which is displayed by the display itself. The ESP microcontroller also has a Wi-Fi connection. This connection is used to retrieve certain information from the internet, like time and weather. Furthermore, the Wi-Fi connection is used to also connect a user interface, a Wi-Fi user interface, which I will demo in just a few minutes. Later in this video, I will explain the technological details of the display more in depth. Before I do that, I would like to power on the display and just show how it works. So I plug in here a 12 volt 2 amp power supply. As you can see, the LEDs start flickering, and then I switch on the motor and the disc starts spinning. And there's also some display already. As you can see, the image of the display is flickering. Unfortunately, this is an artifact of the camera. The camera has a certain frame grabbing rate, and that frame grabbing rate now interferes with the rotation of the disc. So each frame which is taken by the video camera only captures a fraction of the image. It is not the full image in every frame. And because of that, there is this flickering. If I look at the display image with my naked eye, it's actually pretty stable, and there's only a little flickering. I can certainly see the movement and of the spinning disc, but that's not disturbing. So, as you can see, the display images, first of all, here the name router 48. This is the SSID of my local Wi-Fi. Secondly, down here there is an IP address, and that is the IP address of the ESP microcontroller. Now let's use that IP address to talk to the microcontroller, and to do this I have here my mobile phone, and as you can see I entered the IP address up here and just push open, and this is the user interface of my rotating display. There's first of all a adjustment here for the brightness, so I can make it a little bit brighter. It's too bright now for the video camera, so I turn it down again to 55%. Then I can select a mode of operation. Right now it's set to IP address, and I switch here to an analog clock, and it displays here a very simple analog time clock. Then there's a digital clock, which gives me the time, including seconds, but also the date and the day of the week. This next mode is I call it logo clock. It's basically time again. Now the time is a little bit larger, and there's a graphic down here which is kind of a logo. It's very easy to exchange this logo by loading a file to the display. I will show you later how that can be done. Then there is a weather screen. Now the microcontroller retrieves weather information for my town and displays it here. So there's again the time, and as you can see here, it's partly cloudy, 27 degrees centigrade and 42% humidity. The last mode is just an image mode. Here I can display a certain image, nice flower. Nothing more to explain. The other buttons down here are used for the configuration of the display. So there is a first screen for configuring the weather information. I use openweathermap.org. You can get a free access code when you register on openweathermap.org, and that access code is a so-called API key which you enter here. You enter your town and the country, and then you're done. There is also a configuration screen for the Wi-Fi. When you power up the system for the first time, you need to enter the SSID of your local Wi-Fi and the password. And then this information will be stored on the microcontroller, and every time you repower it or reboot it, it will use this information to connect. A very useful and important function is a file browser. The ESP has a file disk. It's relatively small, but it can be used to store information permanently, like images, for example, this flower, but also parameters like the API key for the weather server, but also other information. And this file browser displays all the files which are on that flash disk. The black entries are folders. So for example, there is the HTML folder. This folder has all the HTML files for the web interface. So for example, here the config weather HTML, that is the HTML file for the page which we looked at before. There's CSS information and images behind, and some other stuff, and also here the JavaScripts. So I can go back here with the two dots, and that's basically it. There's also a preview function. So for example, that's the file here for the flower, and I can see it here. Down here, I have certain functionality to upload new files from the mobile phone to the microcontroller, to download files from the microcontroller to the mobile phone. I can make new directories, I can rename directories or files, delete, copy, move. So it's really everything you need to arrange the file system. And then the last function is the image manager. I will not explain all functionality of this. Basically, the idea is that up here I can select a certain file. So let's say this one, that's the logo which I used for my logo clock. And now I can assign this file here to that image, right, to the image mode. Select image. And here we go. You can also upload certain images from the mobile phone to the file disk of the microcontroller. All that functionality is available. That's basically all, and I believe it's really a nice functionality. You can think of more screens. It's relatively easy to modify or add the screens, as you will see when I talk about the software. Okay, so much about the demo. And I now switch off the display by disconnecting it from power. And in the next part of this video, I would now like to talk about the technology which is behind it. And there are some interesting aspects, as you will see. So first of all, I take this thing apart and I have to loosen these two screws here because these two screws hold the display board on the CD tray. So that's the first one. And here's the second one. So I take out these two screws. That's it. And now I actually can take this apart. I will talk about the power supply first. And as you can see here on that power supply board, there is this printed coil. And it turned out that this is really crucial because in the first versions of this power supply, I used copper wire to make these coils, and that was just very difficult to reproduce. There were multiple error sources, so I decided to develop this printed circuit with the coils. That's very easy and straightforward to reproduce. You just have to put in the electronics components and it will work. Now let's have a look at the other side. So here on this side there are the components for the wireless power transmission. It's just few components, and here in the middle there are a few components for the control of the motor, so controlling the speed of the motor. I will show the circuit diagram later. That's the power supply. Now let's have a look at the display board. First of all, again, power supply. This here on the power supply PCB, there was this primary coil of this wireless power transmission, and on the back side of the display there's another coil, and that's the secondary coil of that transformer, and that picks up the power which is sent from the power supply. So let's talk about this disk. As you can see, the most important components are the two LED rows. They have 20 LEDs each, in total 40 LEDs. There is the Arduino microcontroller for controlling the LEDs, and there's the ESP. The first challenge I would like to talk about, which I was facing by developing this, was to balance this disk, because it's spinning pretty fast, and if it's not perfectly balanced in terms of mass or weight, then this would vibrate heavily. The only way to avoid this is to move the center of mass of this disk to exactly the middle, because that's the axis of rotation. So how can I move the center of mass to the middle? The way this is done is shown here in this printout. And what you can see here is the disk again, and I drew actually here the axis of symmetry. And as you could probably see, all the components are arranged symmetrically to this axis. So there is a capacitor here, and there's a capacitor on this side. There is a LED row here and another one there. There's one chip here and one chip there. So everything I have twice is arranged symmetrically. But there are components which I only have once. So for example, the Arduino microcontroller or the ESP microcontroller. And so I put those on the axis of symmetry. The result of this mechanical arrangement is that the center of mass of this disk is now somewhere on this axis of symmetry. And it turns out that it's actually about here at this point. Now I need to move it to the middle so that it actually hits the axis of rotation. And to do this, I'm using two counterweights. It's actually, one would be sufficient if it was exactly on the axis of symmetry, but as there's no space to put the mass, I'm using two. Yeah? So they are balanced according here to the axis of symmetry, but they shift now the center of mass exactly here to this point. As you can see here on the disk, I have two nuts on each of these M2 screws, and that's the perfect balancing that I need. The second challenge I would like to talk about is the resolution of the display. You might wonder why I'm using two LED rows, and there's a very simple reason for that. I wanted to increase the resolution. Now, if you look at a LED more in detail, you will see that the LED has a width of about 2 millimeters, so 2 millimeters each. But the LED itself, so the spot that emits the light, has only a diameter of about 1 millimeter. So if you put a couple of LEDs next to each other, there will always be a spacing between these bright spots. And that spacing is exactly 1 millimeter. So there's 1 millimeter of light and 1 millimeter gap, and then another 1 millimeter of light. And the idea to resolve this is very simple. This is why I'm using the two LED rows, and they are displaced radially by exactly 1 millimeter. Yeah. So this LED here is exactly at the outside, so it hits here the outer circle, and the first LED in this row actually is 1 millimeter towards the middle. And so there is an alternate order, if you like. So this is LED number 1, this is LED number 2, 3, 4, 5, and so on. So that's the idea behind the two LED rows. Before we go into the electronics, one more mechanical thing. When I use this display, it's very critical to have a very stable triggering signal for the LEDs. Why is that? Well, as this thing is spinning, I have to make sure that the LEDs emit their information at exactly the right point in time and the right point in space. In order to achieve this, I need a trigger signal every time that disk actually reaches one specific point. It doesn't matter which point it is, but it needs to have a reference. To do this, I'm using a Hall sensor, which is a magnetic sensor. It's difficult to see, it's this little black spot down here. It's this component, which is the Hall sensor. This Hall sensor is activated by a magnet, and that magnet actually sits right here. So as you can see, that's magnetic. And now if that disk spins and comes here in the vicinity of the magnet, I get a trigger signal. It turns out that this Hall sensor trigger is extremely stable, and that gives me the stability of the LED image that I need. So much about the mechanical setup. In the next section, I would like to talk about the electronics. And this is the electronics schematics, which shows the two parts, the power supply and the rotating display. On the power supply side, I have the Royer converter. That is the converter that wirelessly transmits the power from the power supply board to the display board. Royer is the inventor of that scheme. I will talk about that in a few minutes. The second part of the power supply here is the speed control for the motor. It turned out that pulse width modulation, which I planned initially, is not the best solution, and I'm just using a voltage control for the motor. Now, this is the display itself, the Arduino Nano. I'm using the SPI port, which is a serial interface, to send the LED data to shift registers. These shift registers now parallelize the serial stream of data, and they then switch on and off the LEDs. I have 8-bit shift registers, 40 LEDs, so I need 5 shift registers, and this is exactly what I have. 1, 2, 3, 4, 5. Then there is the Hall sensor. This is just connected here to one of the ports of the Arduino Nano. The ESP8266 is communicating via a I2C bus with the Arduino Nano. And as I was explaining before, the ESP microcontroller has a Wi-Fi connection to the internet. So that's all which is needed for this rotating display. I would like to come back to the power supply and a little bit talk about the electronics. So the Royer converter is shown here in this diagram. I've taken this diagram from a very good article on microcontroller.net. So search for microcontroller.net and Royer, and then you will get an article. It's written in German, but it's really excellent. The Royer converter works like this. There is this coil here, which consists of 2 halves. And then I have a capacitor here, which together with the coil actually makes up a resonant circuit with a resonant frequency of 120 kilohertz. That is the frequency of this oscillator, and that's also the frequency of the wireless power transmission. Now, let's assume that this transistor here is switched on. Then there is a current flowing through this half of the coil, and I induce a voltage here on this with this reference coil. And that voltage now switches on the other transistor. So there will be a current flowing through the second half of the coil. This transistor is switched off at that point in time. And then it goes forth and back, and there's an oscillation here between these 2 transistors. It's a high power oscillation. This capacitor here is really critical. It needs a high quality because the current is really high. That is the Royer converter, very stable. The challenge, as I was explaining, is this relatively complex coil. And this is why I developed the printed circuit as explained in the beginning. The other part is the voltage regulator for the motor speed. The motor has specification of 1.7 to 6 volts. And that's exactly what I generate here with the LM317 voltage regulator, and there's this potentiometer to adjust the voltage. So let's move on to the circuit diagram of the display. It's a little bit busy. If you want to have a closer look, please download this from my GitHub page. I will just very high level explain what is here on this sheet. So first of all, there is the Arduino Nano down here. These lines are the SPI port, which are connected to these 5 shift registers. These shift registers, they give out the information for the LEDs, which are up here and up there. The LEDs also have serial resistors which basically adjust the current. Then there is the other microcontroller, the ESP8266. It only has few connections down here, which are used for the I2C bus, which communicates here with the Arduino Nano. And the very same connection is also used for communication with the computer if you program the 8266. For programming, there is a little connector, a female connector for a level converter, FT232 level converter, and there you can connect the computer and program the ESP. Programming the Arduino is easy because it has a connector built in. This one here is the Hall sensor. These are the rectifiers. That's the little secondary coil of my transformer. So that is the circuit diagram of the display board. Now I would like to talk about the timing of the LEDs, because this is really interesting how it works, and I believe that's also kind of unique for this display. So first of all, there is this trigger signal here of the Hall sensor. I was explaining that before. So for each full turn, I get a trigger signal. That trigger signal triggers an interrupt routine. That's INT 0. That interrupt routine, I start a timer 1. So I set a certain value to timer 1. And what that does is that now timer 1 starts counting. It starts here at 0 and counts up to the value which was programmed. And this timer reloads automatically, which is very critical. So there's no delay if the microcontroller is busy. It will restart with exactly the period which it was programmed for. Every time that counter reaches now the programmed value, it triggers a second interrupt routine. That's INT 1. And this second interrupt routine now outputs the data to the LEDs through the SPI interface. So with every timer 1 event, I output a new row of LED information. And that, in the end, gives me the image of the display. There's one more thing here which is interesting, and that is the brightness control of the LEDs. There is a, I would call it threshold function of timer 1. So you can load a second value to timer 1, and every time that value is exceeded with a count value, an output pin of the Arduino switches to 0. And this is the result of that. I would call it kind of a pulse width modulation, but it's really synchronized with the LED rows. So the end of the story is that my LEDs will only be turned on when this signal is 0. And now I can adjust the time the LEDs are switched on. So I load the certain LED information, and then I switch on the LEDs only for a certain time. That time can be changed, as you can see here on the right-hand side, where the settings of the counters are different. And then the duty cycle here of the signal is different. And different duty cycle means different time the LEDs are on, and that means different brightness. So, let's talk a little bit about the software of the ESP microcontroller. As I was explaining before, the ESP microcontroller generates the image information. and then sends this information to the Arduino Nano. As you could see, the letters, the text was upright and there was no distortion by the rotating LEDs. The way this is achieved is this. Internally, with the ESP microcontroller, I use a normal rectangular bitmap. This bitmap has 110 times 110 pixels. And now I do a coordinate transformation from this bitmap to the polar coordinate system of the LEDs. So to make this fast, I'm using a lookup table. So I have stored the corresponding values. So for example, for this pixel, there is a certain LED number and a certain angle when this number should be output. That is a very fast transformation, and that allows me to display letters upright, easily readable. That brings me almost to the end. I would like to point out that this development is available for reproduction. So if you would like to build such a clock, please feel free to download all the files, all the information which is needed from my GitHub page. It's public, the repository, and you find everything you need to reproduce this display. However, I would like to ask you for two things. The one is, if you develop this further and would like to distribute your modification, please include a reference to the original files which come from me. And secondly, if you are interested in a commercial use of this display, you are not allowed to do that without a license, so you need to contact me on commercial use. But private use, hobbyists, and also teaching purposes is all for free. Just feel free to use it. I hope you like the design. I hope you like the rotating display. And please leave your comments under this video and let me know what you think.